Hello everyone, welcome to the lecture series on Foundations of Deep Learning, Concepts and Applications. We had started with the explainable AI, and in the previous session we had seen sharp and lime with mathematical foundation and a numerical example. In today's session we will explore guided backpropagation. Let us get started. So, before we go into the testing, let us see if the input data is an image, we are going to build a CNN model. Now, once the model is built, we are going to compile the model and we are going to train the model. And once we complete training the model, we are going to get the training accuracy and the training loss. By looking at the training accuracy and the training loss, we will understand how well the model has trained. Once the model is well trained, the meaning of this is all the kernels at this particular convolution layer and then the weights at fully connected layer, all these are well optimized. Now, once the model is well trained, now what we are going to do? During a testing, we are going to pass an input image. Let us assume this is the input image that is being passed during a testing phase. Now, when an image is passed to the trained CNN model, the image will go through the entire this architecture, that is the image will pass through the entire CNN model, where once it reaches the early layers, early CNN convolutional layers, the convolution layer will detect the edges. Then as the image will propagate forward or move forward, the next convolution layers will focus on detecting the texture. So, later or the deeper convolutional layers will help in detecting the object parts. Then you are going to pass the feature maps to a flattened layer. From the flattened layer, it enters into an dense layers and finally to the output layer. Now, this entire is the forward pass. At the end of the forward pass, what exactly the model is going to give us? It produces the prediction for the input image that is passed. Now, what is the input image that is passed here? Now, we know that it is a zebra image. Now, what exactly the model has predicted? Suppose if the model predicts it as a zebra, then what is that we will be interested in? We then focus on the class score logit. Now, what exactly is a class score logit here? Now, when an input image is passed, the model has given the prediction here. Suppose if it is an 3 class multi-class where there are 3 classes, we will have 3 neurons at an output layer. Now, for example, if the model has predicted this particular, here is where the probability is very high. Now, what we are going to take, what exactly is the logit here, is the value before we pass it to an activation function. So, logit is an value before an activation, and here the activation that we have used is softmax, and we have used softmax activation function because of multi-class classification problem. Now, we are interested only in this logit, that is the predicted class score, predicted class, and that particular score, and we denote it as YC. Now, the question comes, if the model has predicted it as a zebra, now the most important question that we will be asking is, which are the input pixels, which are the pixels here has actually contributed for model prediction. So, this is the question, which pixel in the input image contributed the most to this class score. Now, when we ask this question to CNN, CNN will not be in a position to answer it. So, therefore, we will be using an explainable AI technique, and that explainable AI technique that we will be using here is a guided backpropagation. Now, what guided backpropagation role here? The guided backpropagation has to answer this particular question. If it has to answer, then guided backpropagation will tell the CNN that compute the gradients, so that with the help of those gradients, I will be in a position to tell which are the input pixels which have contributed the most. So, therefore, what guided backpropagation will do? It instructs the CNN to compute the gradients. Now, one important point that you need to remember here is when the CNN model computes the gradients, here the gradients are not computed to update the weights or bias or to update the kernels. No. Already the model is well trained. To that trained model, we have passed the input image during a testing or an inference time. Therefore, there will not be any, although the CNN model will be doing a backpropagation here, but that backpropagation is only to compute the gradients. And how many times the backpropagation will be done? The backpropagation will be done only a single time. And why exactly we need? It is only to compute the gradients. And how the gradients are computed? What is that we obtained during a forward pass? During forward pass, we obtained a class score, that is YC. Now, we are going to compute the gradient of YC with respect to all the activations in the network till we reach the input. So, which means you will compute the gradients here, you will compute the gradient at a flattened layer, you will compute the gradient even at an convolutional layers meaning convolution, ReLU and pooling. At every of convolution and ReLU, at every of these it is going to compute the gradients. So, this is all what exactly is an introduction to guided backpropagation. So, a formal definition, guided backpropagation is an explainable AI technique that help us to understand which pixels in the input have contributed more for this particular class score. If model has predicted it as a zebra, so then we are only interested to find out which are the input pixels which have contributed more, and how it is doing by computing the gradient of the class score with respect to input image from class score till the input image. So, in the backward pass, it is going to compute the gradients of all the activations until it reaches the input. So, how it is going to do? It is going by modifying some ReLU behavior during a backward pass, that we will explore in the coming slides. So, from this slide, what we are understanding is just a formal definition of guided backpropagation. Now, let us get into the working mechanism. Now, what we are seeing here is this is just one feature map of the forward pass. Now, in the forward pass, we are when an input image is passed to convolution first convolution layer, second convolution layer, and when it reaches the third convolution layer, we are going to obtain the feature maps. Based on how many number of kernels that we have used, we are going to obtain so many number of feature maps. Now, what we are considering here is only one such feature map. Then let us understand what will happen when we consider many. Now, we are only understanding one feature map. So, remember this is one feature map of the last convolution layer. Okay, this feature map, when it is applied onto ReLU, what is the role of ReLU? ReLU is a max of 0, x, where all the negative values will be turned to 0 and positive values will be retained. So, when this is applied to ReLU, when it is passed to ReLU, we are going to obtain this feature map. right. So, this we know it from our week 3 contents. Now, whatever the feature map that we have obtained, once again I am informing you, we are doing it for one feature map currently. Then whatever is the feature map that we have obtained after applying the ReLU, that is passed to a flattened layer. What is the role of a flattened layer? Whatever is the matrix that we have obtained, it is going to convert that into a single vector. From a flattened layer, we are passing it to a dense layers. So, here we have fully connected neural network. Then the last layer at dense, we have an output. So, for a particular input that we have passed, we have obtained the class. The model has given us the prediction. Let us assume the model has predicted it as C, class C, and we are interested only in YC. What is YC? It is a value just before passing it to an activation. Okay. Now, so this is what we have done. The activations have continued to flatten layer. From flatten layer, it went to the dense layer, and then to output layer. And then we focus only on the class score, focus on the class score, that is YC for a particular class. Now, this is what is the forward pass. Now, what we are going to do? We are computing the gradients. Next, we compute the gradients. Now, once we compute the gradient, during a backward pass, the gradient will flow from output layer to dense layers, which means with respect to each of the weights, it is going to compute the gradient. Then the gradient will flow to the flattened layer. Then the gradient will flow to an convolution layer. So, this is what is the backward pass. So, whatever the gradients that we have computed, those gradients are flowing from output layer to the dense layer, from dense layer to the flattened layer, from the flattened layer it is going into a convolutional layers. Now, when the backward pass reaches the convolution layer, that is when the backward pass reaches to this particular feature map, then what is that we are going to do? We have to now compute the gradients here also. Now, how is that we are computing the gradients? We are computing the gradients with respect to YC, by YC with respect to all the values which are there in this feature map. So, if you name this feature map as A, then we are going to compute the gradients for all the values which are there in this, and let us assume it is one of the feature map of the last convolution. Okay. So, what exactly we did? When the backward pass reaches to this last convolution and ReLU layer, the network computes the gradients. Now, how it is going to compute the gradient of the class score YC with respect to all the activations which are there in this particular feature map. So, let us assume it is what this operation it is doing. Now, which means, is it not we are doing this when we apply the gradients on this feature map with respect to every of this value when you compute, let us assume we have obtained this gradient. What we have done? We have completed the forward pass, we have got the YC, that is a predicted class score. Now, we computed the gradients. When we computed the gradients at a dense layers and at a flattened layer, guided backpropagation does not use any of those gradients. Guided backpropagation does not care. Now, when the gradient, when you compute the gradient at a convolutional layer, let us assume this is the gradient that we have obtained for this feature map. Now, once you reach at this particular point, once we obtain this gradient map, this is where the guided backpropagation comes into the play. So, which means when the gradients reaches to an convolutional layer, the to a last convolutional layer, this is where the guided backpropagation play its role. Now, what guided backpropagation will do? It is going to compute two things. What is the first thing it is going to compute? Forward ReLU mask. It is going to compute this, and the next it is going to calculate something called as a backward ReLU mask. So, once the gradients are obtained, guided backpropagation is going to compute two things. One is a forward ReLU mask, second is backward ReLU mask. Now, first let us see what exactly is this forward ReLU mask. I hope it is clear to us where we are. We have backpropagated, we have computed the gradients at a last convolutional layer. Once we reach to this last convolutional layer, we have a feature map already. Now, we have computed the gradient of the class score with respect to every of the values in this feature map, and let us assume this is the value that we have obtained. Once we reach here, guided backpropagation comes into the play. Now, what it is going to do? First, as I said, it is going to calculate the forward ReLU mask. Now, what is a forward ReLU mask? Now, we are here. Now, when in the backpropagation, when we reach to this first step, it has computed the gradient, we have obtained this gradient. Now, what it is going to do is, it is going to see which all are the neurons which are actually positive during the forward pass. What does it mean? Now, this is the forward pass. Now, which are the neurons which are actually positive here? Now, what do you mean by this? All these values are negative. When you pass it to ReLU, it becomes 0, which means the positive neurons are these. These are the positive neurons. So, is it not forward ReLU mask is actually telling which are the neurons which are actually positive during the forward pass. So, if you see here, in the forward pass, these are the neurons which are actually positive. So, that is what is a forward ReLU mask, and what it is identifying? It is identifying which are the neurons which were active in the forward pass. Now, there is one concept here. Look at this, if you observe very carefully, when you reach during a backward pass, when you reach to a convolutional layer, now you are going to look into this particular feature map. First, we are going to compute the gradients. We have obtained this gradient, and when you look into, there is an ReLU also. There is a ReLU here. Now, when there is an ReLU, during a backward pass, are we not going to compute the derivative of this? Are we not calculate the derivative of this? What is the derivative of ReLU? The derivative of ReLU is, if the value is less than or equal to 0, it is 0. If the value is greater than 0, it is 1. So, in other words, forward ReLU mask is nothing but a derivative of ReLU only. So, what exactly is less than or equal to 0? All these are the values which are less than or equal to 0 here. Therefore, the value is 0 here, and any value which is greater than 0, it is 1. So, forward ReLU mask, when you backpropagate, when you reach to an convolutional layer, that is the last convolutional layer, you already have the feature map. Now, on this feature map, the first step, it is going to take the derivative of ReLU. Derivative of ReLU gives us the forward ReLU mask. And forward ReLU mask will help us to understand which are the neurons which were actually active in the forward pass. Next, what the guided backpropagation is going to do? It has already computed this forward ReLU mask, and it has computed you already have the gradients. Now, it is going to do an element wise multiplication. So, forward ReLU mask is actually represented with this notation. It is just the notation which is taken from the original research paper. In the original research paper of guided backpropagation, they named forward ReLU mask with this notation, okay, with this notation. Yeah. So, now whatever is the forward ReLU mask that we have obtained, and then the gradients that we have obtained, we are going to do an element wise multiplication. So, 1 multiplied with -2, we got -2, 0 multiplied with 3 is 0. 1 multiplied with -1, it is -1, so on so forth. So, what is this? This is called forward ReLU mask, and this is the raw gradients which has obtained from backpropagation. And what did we have done here? We have applied forward ReLU mask on this gradient, and then this is called a standard backpropagation through ReLU. Now, what is that we are understanding from this particular matrix? Now, if you look into this matrix, where all we have the values, wherever which is positive in the forward mask. So, if you look, there are values here, there are values here, and there are values here. So, by doing this particular operation, now gradients, which all gradients are there here, only those gradient values are retained which are actually positive during the forward mask or during the forward pass. So, let us see the formally. During a backpropagation, ReLU is actually using the forward ReLU mask to ensure the gradients of flow. Well, these are the gradients. Gradients of flow only those neurons that were active in the forward mask pass. So, only those gradients which were actually positive during the forward pass. So, if you see these, therefore, only these are retained. That is what exactly is a standard backpropagation through ReLU. So, what operation we did? This is a forward ReLU mask, and these are the gradients, and we did element wise multiplication. And this standard backpropagation through ReLU is denoted with this notation, and once again this is just a notation which we have taken it from a standard from the original paper. Now, have we completed the guided backpropagation? The answer is no. We have just computed only what is a guided backpropagation. Guided backpropagation is two rules that are applied. So, one is a standard backpropagation rule, and the second is an deconvolutional rule. So, now what we have completed so far is a standard backpropagation rule, and this is what is the standard backpropagation. Now, let us understand what exactly happens in this deconvolutional rule. So, deconvolutional, what we have done so far, we have backpropagated, we have computed the gradient. So, what we have with us is the gradient. We have this particular gradient with us. Now, what exactly is this deconvolutional rule does? Now, where all there is a negative, so it is going to make it as 0. Now, why we are doing this? Now, in the forward pass, what exactly has happened? Whatever the feature maps that we have obtained, when it is passed to ReLU, all those negative values you made it as 0, and only positive values have moved forward. The same concept is applied here. Now, what we have obtained is the gradient. In this gradient, there are few positives and there are few negatives. Now, what deconvolutional rule does is, wherever there is a negative, don't pass it, make it as 0. Wherever there is a positive, only allow those. So, this is what it is going to do. wherever the gradient is positive, allow it, which means make it as a 1, and wherever the gradients are negative, block it, make it as 0. So, this is what is the backward ReLU mask that we have obtained. So, this mask what we have obtained, this is called backward ReLU mask, and backward ReLU mask is actually denoted with this notation. This is a gradient. The gradients which is greater than 0, make it as 1, and less than or equal to 0, make the value as 0. So, what we have obtained here is a backward ReLU mask. Now, this backward ReLU mask is now applied on this gradient. So, what we are doing, this only this notation is backward ReLU mask, and this is a gradient. So, and this is element wise multiplication. So, now we are taking the backward ReLU mask, and we are taking the gradients, and then we are doing an element wise multiplication. When we do an element wise multiplication, we are obtaining this particular matrix. Now, 0 multiplied with minus 2, it is 0, 1 multiplied with 3, it is 3, 0 multiplied with minus 1, it is 0, so on so forth. So, this is a backward ReLU mask, this is a raw gradient, and what exactly we have obtained, this is the filtered gradient. So, what exactly is happening in the filtered gradients? Only positive gradients are allowed to pass, negative gradients are blocked. So, what we have calculated so far, we have seen the backward standard backpropagation rule in the previous slide. In this particular slide, we have a gradient. On this gradient, we are now computing the backward ReLU mask. What is a backward ReLU mask? Wherever the gradients are negative, don't allow, so make it as 0. Wherever the gradients are positive, only allow those. Therefore, we have obtained this. So, if you recall the concept, if you go back and then look into the previous slide, when we were actually reached to this point, I have told now guided backpropagation will compute two things. One is a forward ReLU mask, and the second is a backward ReLU mask. So, this is how it is computing the backward ReLU mask. And whatever it has computed, this we call it as an deconvolutional net rule, deconv net rule. So, now we have computed this separately. The next step what we are going to do is, we are combining the standard backpropagation rule and then a deconv net rule. So, this is a standard backpropagation and this is a deconv net rule, and we have seen this separately. But ideally, if you see, once the gradients have been gradient is computed, we have one matrix, gradient matrix or the gradient feature map, that on that gradient we have computed the forward ReLU mask and we have computed the backward ReLU mask, and that is applied onto this gradient. So, what we have done, we have computed the forward ReLU mask and we have computed the backward ReLU mask, and these two are then applied onto the gradient. So, you see, although there are two here, that does not mean there are two times. No, it is being done simultaneously. Therefore, the final equation looks this way, because onto this gradient the forward ReLU mask, onto this gradient the backward ReLU mask, and this is the gradient. Now, we are going to take each of these matrix and we are going to perform an element wise multiplication. This is forward ReLU mask, this is a backward ReLU mask, and these are the gradients. We are going to do an multiplication, and this is the matrix that we have obtained. And how is that we are obtaining? You see, 1 into 0 into minus 2, we have obtained 0. So, we are performing an element wise multiplication, and this is the matrix that we have obtained. And when we look into this matrix, we call this as an guided gradient map. Whatever the matrix that we have obtained here, we call it as a guided gradient map. Have we completed the guided backpropagation? The answer is no. What we have done so far is we have applied a guided backpropagation to the backward in the backward pass, and in the backward pass, when you have reached to an final convolutional layer to one of the feature map, what we have applied is we have reached to this point. Guided backpropagation. This is only for one feature map during backward pass. So, with this, I hope you have understood how guided backpropagation works, although we have still not completed it, but what we have done is how guided backpropagation works. And we have seen this applying only to one feature map. With this, let us see when we apply to all the, now let us see the complete working mechanism. So, we have one input image which is of size 7 cross 7, just for understanding, intentionally very low dimensions are kept, that is passed to a convolutional layer. Now, here again for understanding, I am taking only one convolutional layer. Let us see moving forward how it works for multiple. Now, what you are seeing here is a CNN model which is having only one convolutional layer. When it is passed to one convolutional layer, let us assume there are 5 kernels. When there are 5 kernels, we are going to obtain 5 feature maps. These 5 feature maps are passed to ReLU, and then we are obtaining the feature maps after ReLU or post ReLU. These feature maps are passed to flattened layer, are passed to dense layers, and then we are passing it to we are at the output layer, we are going to get the predicted class. Now, for that predicted class, we are computing, we are taking YC. So, this exactly is the forward pass from input image to convolution, and then to ReLU, then flatten, dense, and then we are obtaining we are looking into this class logit. Now, let us see what happens in the backward. In the backward pass, CNN is computing the gradients here, but with respect to YC, all of gradient of YC with respect to the weights at a dense layer and at a flattened layer. Now, it is computing the gradients at a feature map also. What we have seen so far is for this one feature map, when you compute the gradients, when you apply the guided backpropagation, we have obtained the guided gradient map. This is what we have seen so far. For one feature map we have seen. Now, the same concept is applied to each of this feature map. On this feature map, when the gradients are computed, when you apply guided backpropagation, we get one gradient map, guided gradient map. On this, when you apply the gradients, you get one gradient map. On this, when you apply guided backpropagation, you get guided gradient map. So, on this, so on each of these feature maps, when you apply the guided backpropagation, we are obtaining the guided gradient maps. What we have seen so far is just one feature map, and we obtained one guided gradient. Now, when we apply it to rest, we are going to obtain these many guided gradient maps. So, have we completed the calculation? No, because it will go till the input till the input. So, in the forward mask we have seen in the forward pass we have come up till here. So, now when you pass, you have kernels also. because in order to reach to the input, you have to pass through this kernels also. So, now what you are going to do, you have taken this guided gradient map, and then there are kernels. Now, you are not going in the forward pass, we are in the backward pass. When we are in the backward pass, what operation we are going to do is, we are going to do a transposed convolution. When you are doing a transposed convolution, what is convolution operation? You have a feature map and you have a kernel, and the kernel will go through the entire and you get the feature map. This is an input image. Onto this input image, you will take the kernel, you will pass that kernel onto this and you get the feature map. Yes, this is what will happen in the forward. But when you are in the backward, what you have obtained is a guided gradient map. Onto this, when you apply the kernel, you are going to take the flipped kernel. What do you mean by flipped kernel? You are going to rotate all the values by 180 degrees and you get one matrix. That is the flipped kernel. Now, you are going to perform a transposed convolution operation, and when you perform, what is the size? 5 cross 5, and the kernel is 3 cross 3. When you do a transposed convolution for this kernel and on this gradient, you get this. This kernel on this, you are going to obtain this. This kernel with this, you will obtain. So, for each of the kernel and with its associated this particular matrix, we obtain a transposed convolution outputs. So, we have obtained this transposed convolution. Now, where have we reached? From the backpropagation, in the backpropagation, we have now reaching to input. We have completed the entire convolution operation in the backward pass when the gradients are obtained, when the guided backpropagation is applied. Now, we have reached to this particular stage. Now, what we have obtained here is a transposed convolution output. How did we do? What operation we did? We took the G and we multiplied it with the flipped kernel. Now, we need not have to manually code this during a backpropagation. Automatically the framework will does this. Now, what we have obtained is now you are reaching the input. If you observe, we had taken the size 7 cross 7. Finally, we have reached back to 7 cross 7. Now, you can ask the question, when 7 cross 7, when it is passed to 2 and 5 kernels, each of size 3 cross 3, we ended up in getting 5 cross 5 feature map, where there is no padding applied. Therefore, the dimension has reduced. Now, when you are back propagating, you should ultimately reach back to the input size, right? So, here we have reached back to input size 7 cross 7. How did we do? What operation happened? Is the transposed convolution operation that has taken place. Now, you have obtained 5 such matrix. We are going to do element wise addition. When we perform element wise addition, element of all these, when you add, you are going to get this value. When you add each of these elements, when you add, you get this value. Now, what we are discussing? We are discussing the guided back propagation. What is guided back propagation? It has to tell which are the features which are important for model, which are the pixels which are important for model prediction. Now, we have reached to an input. Here you will have, in each of these locations we will have the values. Wherever the value is very high, it means it is that particular pixel which has contributed more for model prediction. Wherever the value is less, it is that pixel which has contributed less. If there is 0, it means that particular pixel value has not contributed. So, whatever we have obtained here, this is the final guided gradient map, and this is where you will see which are the higher the value, higher the pixel values which are important. So, although this is a very heavy topic, but understand it is very simple because what you have seen in the initial slides is when it is applied onto one matrix, you have obtained one guided gradient map. Now, it is just not one, you have 5. So, when it is applied on each of these, we are going to get 5 such guided gradient maps. Then you are going backward till the input. When you go backward, you are now at a convolution step, and in the backward you are going to do a transposed convolution. What is a transposed convolution? First the kernels are flipped, and then you are going to do an multiplication. What multiplication you will understand now. And then you are going to obtain this matrix, these set of matrix where the size has increased. Now, you ultimately there is only one input that we have considered here. Now, you have 5 such matrix. So, what you are going to do? You will perform an element wise, you will add up each of these and you will end up getting one matrix. In that, wherever the values are high, which means those pixel values have contributed. So, this is a backward pass for an single CNN model. Okay. Now, let us see what exactly is this transposed convolution. Here in our example, we had taken 5 cross 5 as a G. The G size is 5 cross 5 and the kernel size is 3 cross 3. For simplicity, for understanding how this transposed convolution is happening, we are taking a simple example where G size is 2 cross 2 and then kernel size is 2 cross 2. Okay. What is our original G? The original G value what we have taken is 5 cross 5 and the kernel what we have taken is 3 cross 3. So, this is 5 cross 5, this is 3 cross 3. So, for understanding, let us see with the 2 cross 2 example. The very first step is the kernel should be flipped. So, here flipped is rotating 180 degrees. So, if the original kernel is 1, 2, 3, 4, on rotation you are going to get this kernel. Okay. Now, what operation we are doing? Onto this G, we will apply this kernel. Okay. So, now let us see how it is going to, what is the formula, what will be the output size? The output size is input plus kernel minus 1. Here input here is G. Now, what is G? G is 2. Right, and the kernel size is here is also 2 minus 1. So, 2 plus 2 minus 1 is 2 plus 2 is 4, 4 minus 1 is 3. So, the size of the output size what we are going to obtain is 3 cross 3. So, now let us write this 3 cross 3. Originally this will be the 3 cross 3 size. Okay. Now, what exactly is a transposed convolution? Take the first element 1 that gets multiplied with this kernel, this kernel. So, 1 into 4 is 4, 1 into 3 is 3, 1 into 2 is 2, 1 into 1 is 1. Look at in which position we have placed all these values. Wherever the input position is, here the first input we are considering. Therefore, and here the size is 2 cross 2. Therefore, in this place you are going to put the result of this calculation. Now, which position you are considering? Second is this, we are now considering this 2. 2 multiplied with this kernel. And where is the position? The position is right top. Therefore, in this right top you are going to place the calculation 2 into 4, 4 2s are 8, then 2 to 4, 3 into 2 6, 2 into 1 is 2. Likewise, you will do for 0 and you will do for 1. So, when you do for 0, this is the result that we have obtained. When you do it for 1, this is the result that we have obtained. Now, what are these 4 G1, G2, G3, G4? If you go back, these are this G, capital G is what we have obtained is this. That is what the G's that we have obtained. Now, the final what we are doing, we are going to perform an addition here. So, here we are performing the addition. So, how are we performing the addition? So, look into 4 plus 0 plus 0 plus 0 is 4. Then 3 plus 8 plus 0 plus 0 is 8 plus 3, 11. Then you will take these position and then you will add, it is 6. So, likewise you will do element wise addition and you are going to get this. So, now what you have obtained this final G, here this final G is this, whatever the value. Now, here whichever the value is very high. So, here the value is very high, which means this pixel has contributed more for model prediction than this. Then here we have. So, it is going to highlight which are the pixels that has contributed more. Now, you can ask, but our input size in the previous slide, the G value is 5 cross 5 and the kernel what we have taken is 3 cross 3. So, substitute back into this formula 5 plus 3 minus 1 into 5 plus 3 minus 1. So, 8 minus 1 is 7, 8 minus 1 is 7, 7 cross 7. So, in 7 cross 7 initially all the values will be 0. Then which you will take the first element, multiply it with 3 cross 3 kernel and then you will place those values here. Then you will take the second element, multiply it with that kernel, you will place those values here and so on so forth. You will add up all of these and then finally you will get these many G's, you will get these many capital G notation and you will add up all of these and you will get the final guided gradient map. So, what we have seen here is the entire working mechanism of guided backpropagation for a single convolution layer. Now, what if you have more layers? Let us take this example. However, this is an additional slide. Otherwise, here we have completed the working mechanism of guided backpropagation. What you are going to see here is when there are multiple convolutional layers, how it is going to perform. So, this is an input image that we have. So, when it comes to this particular example, just understand only on the concept, let us not look into the size. Okay. So, this is just to show you how when multiple convolutions are there. So, this when input is passed to first convolution which has 3 kernels, you are going to obtain 3 feature maps that we know very well. So, these feature maps are now passed to, in the second convolution you are using 5 kernels. So, how do you get 5 kernels? When this kernel is applied onto all of these feature maps, you get this matrix. So, when the kernel is applied on this, you get 1 feature map. When the kernel is applied on this, you get 1 more. When you apply on this, finally you will do an element wise addition and then you get this. So, this concept is exactly, we have seen this during our week 3, how convolution operation takes place when there are multiple kernels that are used. So, you are when input is passed to first convolution which is having 3 kernels, we got 3 feature map. When those 3 feature maps are passed to 5 kernels, we have obtained 5 feature maps. So, now this is passed to flatten layer, output layer, we are going to get one prediction. From that prediction we are computing the gradients. So, all that we have already seen it. So, we are computing the backward pass. in the backward pass, this is where up till now we have seen. I hope this whole you have understood from the previous one. Now, what exactly the operation that has taken place here? Whatever the feature map that we have considered during the forward pass, those values should be greater than 0. And what is this? This is a forward ReLU mask. And what is this? The gradients should be greater than 0. This is a backward ReLU mask. And these are the actual gradients. So, when you compute this, we are going to get one guided gradient map. So, now you are doing it for all. So, therefore, the general notations we are now keeping in general. Here, what you are seeing is we have used two convolution. This is conv 1, this is a conv 2. So, we are at a second layer in the backward pass. We are in the in the backward, this is the first convolution layer, but otherwise this is in the forward pass we are at a second convolution. So, that is where you are seeing the number 2 here. So, I hope this is clear to us. Now, from this 5 gradients that you have obtained, have you reached to input? We have still not reached to input. If you would have reached to input, then you will add up each of these elements. But here we are not adding these, because to reach to input you have to still pass to one more convolution. Then what you are going to do? You will now compute the gradients. So, this is the input which has to now, this entire is the input now which has to pass to the first convolution. So, now what you will do? You will compute the gradients. How are we computing the incoming gradients? Now, you see, you will take this G21, these you will compute the gradients with respect to this feature map. You will take this gradient, you will compute with this feature map, this gradient with this feature map. So, you look at this formula, what we are doing, then you add up all of these, you get R1. Then you take this particular gradient, and you with respect to this you will compute the gradient. You will take these values, you compute the gradient with respect to this. So, look into this formula and look into this. Finally, we are obtaining these incoming gradients. So, what did we do? It is very simple concept. We have from here we have to now pass it to this convolution. When you have to pass to this convolution, during backpropagation you have to compute the gradients. So, how are we computing the gradients? Now, in the backpropagation, this is where we have reached. So, with respect to each of this feature map, you are computing the gradients. So, now this is the incoming gradient. So, on to this incoming gradient, you will now apply onto this feature map. So, look at the what backpropagation, what guided backpropagation happens at this particular one. So, here we have a feature map. That feature map, this feature map values which are greater than 0, this is forward ReLU mask, and whatever the incoming gradient that we are getting. So, that is incoming gradient. In this incoming gradient, if there are any values which are greater than 0, retain that, less than 0, mask it. So, this is your backward ReLU mask, and you are obtaining G11. Similar way you will get G12, G13. Then you will apply it on a flipped kernel, you are going to get these transposed convolution outputs. Finally, at this you are going to add up all of these, and here is where it will highlight which are the pixel values which are important during model prediction. So, the whole concept is being explained in the initial slides itself. Later what we have done is how it will happen on the all the features. Then we have seen you know how it will work for one layer of convolution. This is the slide where how it performs at multiple. So, I just want you to focus on this part. Up till here it is the same, as the previous one. But when it comes to the first convolution layer, look at what is being passed. It is this, and how are we getting this? Look into this calculation. So, very carefully take a pen and book, calculate. You will be able to understand this, although it looks very heavy, but the concept is really simple. So, finally, this is the output that we get during a guided backpropagation. Here the features are not very clear, but when you apply the guided backpropagation, it is going to highlight which are the features which are more important. So, this is an input image, this is the output of guided backpropagation. So, this is the input image, these are the outputs of guided backpropagation. So, it is going to highlight which are the input pixels that have contributed more for model prediction. If you look into, we can able to see the shape. So, we can able to see the shape. So, let me erase, you can able to see it clearly. So, here we are not able to see the zebra outline properly, but here we can able to see the outlines very clearly. So, this is what is a guided backpropagation. So, in the next session we will see GradCam and CAMS. Thank you.